Cecilia, and this is my physics lab 3. So for the introduction, we had to apply Newton's second law and use its parallel and perpendicular forces in order to find the mass of the black hole and the initial velocity needed to join an orbit around the black hole using a computational model where the system for part 1 is a star and the system for part 2 is a ship. And some important information to know is Newton's second law, which is this equation, which is F naught divided into its parallel and perpendicular forces, and where the parallel force is equal to this equation, which controls the direction, and the perpendicular force is equal to all of this, which controls the speed. So for the computational model for part 1, I inputted my email, which gave us the data that we were going to use, and then I changed these 3 values depending on what we were going to do, which is 1 day, and then the mass of the star and the gravitational constant. And then for the control loop, the calculation loop, I found the p initial and the p final by doing the mass of the star times the v initial and the v final respectively. And then for the change in velocity and the change in momentum, I did its final minus its initial values, as we can see here. And then for dp dt, I did delta p is equal to divided by delta t is equal to dp dt, as we had established before with the equation as well, and that is also equal to f net. And we are, in order to find dp dt parallel or f net parallel, which is the same thing, we had to find p hat and the change in the magnitude of p over dt, which is p initial over its magnitude, and then magnitude of p final minus magnitude of p initial divided by delta t, which is equal to f net parallel, and then f net perpendicular is the difference between dp dt and dp dt parallel. So to actually find the mass of the black hole, I did rearrange the gravitational force equation in order to equal m, the small m, with the big M being the star. And I found that the mass of the black hole was this value, and I got this computational model out of the code, and I found that F net is the blue arrow, F parallel is the pink one, and F perpendicular is the orange one, as we can see. And I got these values for each of them. So what does it mean? Discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum. So as we can see in the code, I did F net is equal to dp dt, so we can see that they're essentially the same. The only difference is that they can be found in different ways, and the change in momentum can be observed, while the F net needs a lot more information to be calculated. The change in momentum is also calculated, but it can also be observed in different ways, so it's essentially the same but also a little bit different. And I forgot to mention the errors in the code, so there might have been some rounding errors with the values that we had established, like the gravitational constant, the mass of the star, the time, etc., but also maybe some problems with the computational code, as it's also always not 100% accurate. So for the computational model for the second part of the lab, I established that this was my initial velocity in the x and the y direction respectively, in order to not crash or be absorbed into the black hole. And then the net force, I essentially did the same thing for each of them, so I'm only gonna explain one. We had to find the difference in position and also the r hat of that vector in order to find the force. So the difference in position, I did the planet minus the black hole's position, and then I found the normal of that vector by using the vector divided by its magnitude, and then I plugged it into the gravitational force equation. And then I did the same thing here, and I added these 2 values to find the force that was acting on the planet, and then I did the same thing in these 2 to find the values that were acting on the ship. And then I used the position and velocity update formulas in order to find the position and velocities of the planet and the ship to find this computational model, which I got right here. And I got that they didn't crash, and as we can see here, the black hole is exerting some kind of force, the gravitational force on the ship, which is making it curve slightly here downwards. And as you can see, it doesn't crash with either the black hole or the planet, as this is still in its orbit and this is going down its own path. So there might have been some errors with this code, like I mentioned prior, with the rounding, but also maybe some equations, as not all these calculations are 100% accurate. There are other forces acting on this that we might not know of, and basically there are a lot of situations that we might not be thinking about when writing the code, but for the basics part of it, they're all here. So what initial velocity would your spaceship need to have in order to enter into some kind of orbit around the black hole? So I tried to change the velocity that I had mentioned prior by increasing it or decreasing it, but every single time I did that, it either crashed into the planet or it was absorbed by the black hole. So I determined that this was probably the best outcome that I have, and it's not a complete orbit, but there is some gravitational influence by the black hole on the ship. So I think that's pretty good enough as we can see the curve here. And it's not perfect, but I did try to increase it and decrease it. And honestly, it didn't really work. It might have induced some errors, but from what I got, this was the best outcome possible. So this was my orbit around the black hole.